So first, some definitions of a weak base. Or sorry, weak acid. Weak acid. We'll start with acids. This is kind of the complementary note that dealt with our strong acids yesterday. And simply compares it to those strong ones. Strong acids are very good at getting rid of their H pluses. They have a very weak connection to those H pluses. Weak acids are not very good at getting rid of their H pluses. If it was a game of keep away of the H plus, then weak acids are not very good players. So they don't ionize very well. Remember, acids, they ionize in water. They're the molecules that lose their H pluses. Weak acids, they don't ionize very well. They only partially ionize. Therefore, they exist primarily as their molecules. And if they only partially ionize, we therefore will have a low concentration of H3O+. It definitely won't be like a 1-to-1 ratio like we did with the strong acids yesterday. And therefore, they would be poor electrolytes, and the reactions would be slow. And so the equilibrium lies to the left. And that's what we want to deal with today. How are we going to then now incorporate these calculations, the pH and the H3O+ and the POH and all that stuff? How can we incorporate that into these weak acid situations? It turns out that we can, again, make a nice little shortcut like we did with the solubility. Now, I think that little shortcut, well, you know what, the solubility shortcut cost us on the common ion effect problem because we all wanted to use the shortcut, right? And sometimes when we learn a shortcut, we rely on it too much, but you guys are bright. I'm now have faith if I teach you a shortcut, you'll be ready this time. So I'm still going to go ahead with showing you the shortcut because I think when you can derive an equation and that equation has function, it's just as powerful to learn how to use that equation in the proper sense. Some teachers and educators believe, oh no, they're just new at learning equilibrium. Make them do the whole thing every time. I disagree with that. I think there's function in learning, in deriving an equation and then knowing when to use that equation. Okay, before we get into the calculations, one more little. Oh, hold on one second. Do I want you to write this? Yeah, let's see here. Example. Let's not write this one. Let's not write this one. I really didn't want you to write it for the strong bases as well, but you guys wrote down so fast that you started to write, so I just had to do it. This is simply just an example of what a weak acid then would be. C2H3O2 is our acetate ion. If you check on the back of your periodic table, I like to write that normally as, right, CH3COO minus is the acetate, H is acetic acid. In this particular notation, the back H is the one that falls off. In this particular notation here, it is the front H that falls off. It's transferred to the water to get us our H3O+. It is an equilibrium situation, but it says here at equilibrium only 3% of the H's have fallen off. Only 3%. Therefore, C2, the acetate ion, has a stronger attraction for the H+ than water. Do I have a mistake in there somewhere? What did I say? Sorry, 1.3%. 1.3%. What that means is the equilibrium lies that way, all right? And that's what makes it weak. It means that there's a lot of carbonic acid, no, not carbonic acid, there's a lot of acetate, goodness gracious, acetic acid molecules. Whew, I'm losing it. There's a lot of acetic acid molecules that exist in the water, and very few of them exist as acetate, all right? It sits to the left. Okay. So let's write down a little brief thing on what are examples of weak acids, and I do want you to write this down. And then we'll get to the calculations. And again, the textbook supplies us with a fair bit of calculations on this, which is excellent. So I do want to get to them fairly quickly. I'll tell you right now that the very last example that I have in this lesson is an example that I didn't used to teach. It wasn't in the old textbook. It's in the new textbook. So I've added it. But in my running around this morning, I haven't had a chance to take a close look at exactly how to do it. I'm pretty sure I remember how to do it, but I'm going to trip over it, which is why I'm tripping over my words already. You guys know how that works. When the clock runs low, or if I'm thinking about something else, I trip over every second word. So that's why I'm doing that. But I'll have it figured out by then. I've got it figured out. Actually, I have the book wide open right here so I can check it. It's not a difficult problem. It's just something that the new textbook adds in. Okay, examples of weak acids. Well, we talked about how all the hydrohalic acids, hydrochloric, hydrobromic, hydroiodic, are strong. Those are the exceptions. They are weak. We talked about the oxyacids. If there's more than 2 oxygens greater than the number of hydrogens, it's strong. And so if it doesn't have that requirement, right, if ones that contain equal numbers of ionizable H's and O's or 1 more, right, if it's 2 more, it's strong. So HClO, that's a weak acid. H3PO4, that is a weak acid as well. There's not double the number of O's. And then down here it says carboxylic acids. Carboxylic acids are what we call organic acids. Acetic acid is actually an example of an organic acid, and don't worry so much about that. If I had taught you the organic chemistry unit first, you'd know exactly what that is. You don't have to worry about that right now. All right? Okay, let's then get ready to calculate these H3O pluses and pH, et cetera, et cetera. Let me first define the ionization constant, and as you're writing that down, I'm going to pass out a table that contains many ionization constants. And due to my my considerable ability in running a photocopier, right? Remember how I said the vertical flip? That's the way to go. I've stumbled across another groundbreaking technique. If you double-side the data table, then that will save you a fraction of a second during your test on finding the data, because it doesn't matter what side of the paper that you put up on your desk, you'll have data looking at you every time. So if you print the same thing on both sides of the sheet, it doesn't matter whether you flip your sheet over accidentally, you have the data right in front of you at all times, right? That's time saving right there, right? That has nothing to do with accidentally not shutting off the double siding feature when you photocopy your next photocopy. That's a truly groundbreaking photocopying technique. An extra one, you mean you need 2 more versions of the same thing, or did I just not hand out enough? So that's why you have the same thing on both sides. You can decide whichever side you'd like. Maybe it might be handedness, left-handed or right-handed, I don't know. You can use the left-handed side. What's that? Yeah, put it in there. Here's the deal. You can use this table on your test, all right? Don't write anything on it. But on the exam, I will be providing you with a new version of this, or I will provide you with the Ks in the exam. Okay, The equilibrium constant for a weak acid is called the acid ionization constant, and is symbolized as a Ka, all right? The higher the value of the Ka, the stronger the acid. It's very much like looking at the KSP, right? The KSP is a number that relates how well a solid dissolves. And I said the higher the KSP, usually that means it's more soluble. In this case, when we're talking about acids, we're talking about the H's falling off. So this Ka directly tells us how many of the H's falls off. It's going to, with a mathematical equation, it's going to tell us exactly how strong that acid's going to be. So if we look at the top of the table, you can choose whichever side of the page you'd like, you'll notice we have things at the top like perchloric acid, HClO4. Notice 1 H and 4 O's. That's a strong acid. Look at the K value, 2.0 times 10 to the 7. Hopefully we can still see those numbers. This comes from an old textbook, like 2 or 3 textbooks back, but it's an excellent table. Can you all see there 2.0 times 10 to the 7? All right. And as we work our way down, H2SO4, again, 2 O's greater than the number of H's. That counts as a strong acid, and notice its Ka, 1.0 times 10 to the 3. Those are big. Those are existing to the right. We're assuming they're all falling off. Even nitric acid, HNO3, counts as strong. What is that? 2.2 times 10 to the 1. And hydrochloric acid, that one is very strong, 1 times 10 to the 6. So those ones at the top are very strong. Now, in the note yesterday, I told you, please memorize these. But you know what? There's a list of them right there. If you understand that a big Ka means that a lot of H's fall off, then you can just look at that and say, hey, that thing is strong. That's why I like you to be able to use this on a test. I think this is a useful bit of data to help you determine what's strong and what's not. As we move down, you'll notice that the power of 10 decreases with hydrogen sulfate, and then down to phosphoric acid, 7.5 times 10 to the minus 3. And it's not necessarily in order of strength, but it kind of, then just kind of meanders along there to varying strengths and weaknesses. So there's no necessarily order to this. Is it alphabetical? No. Is it by atom? Not necessarily. There's really not a whole lot of rhyme or reason. But you'll notice if we pick ammonium, not ammonium, I want nitrous acid, 4.6 times 10 to the minus 4, hydrogen cyanide, 4.9 times 10 to the minus 10. So you can see there we have varying degrees of strength. And this is going to become very useful in order for us to determine exactly how much H3O plus is produced. Okay, so let's do the shortcut. Now, when dealing with acid reactions and weak acids, and I mentioned this yesterday, only consider 1 H falling off at a time, even though it might be something like H3PO4. We only look at 1 H at a time, and that's because the K changes for the next H. So we can't do an equilibrium that takes all the H's off. Let me show you an example. Let's look for phosphoric acid. There it is on the table. Some of you are writing. As you're done writing, you can look. It looks like it's about 5 or 6 down. And you'll notice H3PO4. And to remove that first H, the ionization constant is 7.5 times 10 to the minus 3. Now, if you move down, you will find a dihydrogen phosphate. It's actually the next one right in line. This K is the K needed to remove the next H, because we only take 1 H off at a time. Different H's have different holds, and therefore different K values. So the K for dihydrogen phosphate is 6.2 times 10 to the minus 8. You'll notice the second H is a lot weaker than the first H. And if we keep moving down to hydrogen phosphate, 2.2 times 10 to the minus 13. Very weak to remove that last H. All right? So we'll talk about how that comes into play. But at this point, you need to only consider 1 H falling off at a time when we deal with these problems. Which means I don't really need to write down what type of acid it is. The actual name of the molecule and the actual chemical formula is really not useful. All we need to think of is an H stuck to an ion that will then be donated to a water to make H3O plus, and then leave me with some kind of conjugate base. Whether that's an acetate, or whether that's a dihydrogen phosphate, or whether that's a chloride or a sulfate, it doesn't matter what the A is. This essentially is any weak acid, and this here is its conjugate base. And that's all that really matters. Which means we can come up with a general equation for all weak acids. And we're going to do that like we know how for any type of equilibrium situation. We're going to use an ice table. Now, in this particular ice table, the weak acid is reacting with liquid water, and water is a liquid, and therefore it doesn't come into play. Now, if I'm doing this as a general sense, I'm going to have a certain concentration of the acid, a certain molarity of the acid that I'm going to start with. Because I'm doing this as a general sense, I'm going to call this square brackets HA. In other words, the concentration of the acid that I'm starting with. I could have put in there a different variable. I can't use X, right, because I'm going to use X in the next line, but I think this is not a bad way to represent it. This is the initial concentration. I couldn't put a little I there, but I'm hoping we'll just understand once we get to the bottom. This is my starting concentration of my acid. 0, 0. None of the H's have fallen off yet. So we've put the weak acid into the water, and we've said, hold on, don't start the game. Hang on to your H's, and then we blow the whistle. Boop, the game begins. They get rid of their H's. They play the game. Equilibrium goes on. We tell them to stop so we can count things. We have minus X because it's lost a few H's. We have X, and we have X. I want to go back up and address one thing at this time. Again, we're talking here about pure water, okay? That number right there is 0 because it's in pure water. This is to determine a calculation for pure water. There's going to be a common ion effect type situation. We call them buffers. We'll be learning about that later on. In biology, you may have learned about buffers, right? The common ion equivalent for an acid is called a buffer, and that's where this number is not 0. We'll get to that next week. Okay, so finishing off our ice table. HA minus X, X, X. Ka. I failed to write this last time, so I'm going to make sure I do it with this derivation. Let's write it out completely. Concentration of H3O plus times the concentration of the conjugate base over the concentration of, now I got to be, see, here's where I'm in trouble. Concentration of HA, and I'm now going to put this little initial here. I got to put this little I here. Put a little I right there, because I have to distinguish it between it. Okay? This at equilibrium, X, X. In this case, the initial concentration, HA initial, minus X. That's equal to Ka. I'll bring those two X's together. Ka X squared over HA initial minus X. If I bring this through and multiply it through, I'm going to have an X, I'm going to have an X squared, and I'm going to have a number. This is going to be a quadratic. We don't want to have to deal with quadratics. So what do we do before what's the last resort before we do a quadratic? Check for the approximation. And here's where our derivation is going to be very important. For a weak acid, the approximation is good. All right? A weak acid, by definition, has a small Ka. It means that if I take that HA initial over the small Ka of a weak acid, that should get me a big number. You should keep an eye out for it though. When you're dealing with the K, if you see that it's getting close to the value of that HA initial, you might not be able to use this shortcut that I'm deriving here. So now let's continue with the shortcut. If the approximation is good, which X can I get rid of? Yep, the minus X. That's approximately equal to 0. That gives me, and I'm running kind of out of space here, but that's okay, Ka is equal to X squared over the initial concentration of the acid. Now, that's sometimes a useful equation right there. Actually, no, that one's not useful yet. I'm going to go to a better one here. Let's solve for X. Ka HA initial, and because I'm running out of room, I'm going to do the last step. What's the last thing I'm going to have to do to get this last equation? Take the square root. So X is equal to the square root of the Ka times the HA initial. Okay? Now, what does this get us? Well, if I'm dealing with an acid or a base, the most useful thing that I can measure is pH. So ultimately, I want to get to pH. Ultimately, just like yesterday's questions, I want to figure out the pH of some solution of vinegar, but it's weak, so I need to do it differently. Notice, X is the H3O plus concentration. This is very important. Just like in solubility, where X was the molar solubility, in an acid-base, weak acid-base calculation, in this case the acid, the K is the H3O plus. Now that's really powerful, because now I have an equation that says H3O plus is equal to the root of Ka times HA initial. And that's if it's weak enough. And that right there is the useful one. All right? That means if I have a weak acid and the Ka is such that we can do the approximation, I don't need all this ice table. All I need to do is take the Ka, multiply it by the initial concentration of the acid, take the square root, and I have the H3O plus concentration. If I now then leave it in my calculator and I do negative log answer equals, I've got the pH. Two little equations. Boom, boom. I'm done. If I'm given the pH and I want to solve for the Ka, I could use this equation, but I could just substitute in here H3O plus in there. And I wish I had room to write it. I guess I'll squeeze it into this space right here. Again, you guys can write it down below. But that means that the Ka of a weak acid can be determined by taking the H3O plus, squaring it, and dividing it by the original HA initial. Okay? So that gives us a way of finding the Ka as well. But that's true if it's only really weak. If you came out with a Ka that was fairly big, you'd have to go through the entire ice table in order to solve it, in order to get it. All right? You'd have to have all of the X's. You'd need these numbers in here. If it's not truly weak, then we're back to using this thing right here. Okay? If not weak. So, if not weak. If it's not weak enough. Okay, that's kind of handy. That little equation right there is handy. Don't write it on a piece of paper. Don't write it on your periodic table. There's going to be about 4 more that are like this. So you're going to have to memorize these if you want to use them. and you got to think about where to use them. But that's a handy equation. Let's go ahead and solve some problems. To be honest, I only memorized the one. I only memorized that H3O plus equation, and then I rearrange and solve if I want to get the Ka. It's easier to memorize one and rearrange and solve than to memorize all this stuff. Essentially, if I'm dealing with a problem like this, I'm asking myself, is it weak? If it is, I'm using that one with the square root. And if I find it's not weak, then I got to make a nice table. I got to start from scratch. I'm going to assume that it's weak until I get the Ka, and if it turns out that that Ka is too big, I might have to redo it. Determine the Ka for hypochlorous acid, HClO, if a 0.1 mole solution has a pH of 4.23. So, in this case, I've got the HA initial. What is the HA initial? What is the concentration of the weak acid initially? Yes? 0.1. There it is there. 0.100 moles per liter. I don't normally write all this stuff down. You guys are pretty good at that, but I'll just do it for the first couple. pH. pH is 4.23. What can I get from that? As soon as you see a pH number, you need to think this number. Yep, Tyson? H3O plus. All right. So we want to determine the Ka. I'm going to assume it's a weak acid. I'm going to assume it's weak. It might not be, but then I'll have to start again. But that's what I'm going to do because I want to use my shortcut. I always go with the H3O plus root Ka HA initial. And then I rearrange. That's the way I think it through. I eventually want Ka, so I got to square both sides. H3O plus squared equals Ka HA initial. I got an extra bracket in there. Divide it off. I need H3O plus squared over HA initial is Ka. You could find the H3O plus if you like as a separate thing, but you could even put in here 10 to the exponent negative 4.23 all squared. There's no reason why your calculator can't handle that. And if you're not sure about that, you can do it separately. 0.100 Ka. I'll take a number when you have it. Jess, what do you got? Times 10 to the negative 8. That's sufficiently small that our assumption is good. Okay? Yep. Sorry? It's a K, so no, it doesn't. It technically would. All Ks do, but we never worry about that. Yeah. All right? Determine the percent ionization. Again, a calculation that I didn't used to do, but this textbook likes to do this. Last year, I introduced you to a percentage ionization calculation. It's really just a percentage, right? It essentially is how much H3O plus per HA initial times 100. In other words, how much H3O plus was formed from that initial concentration of acid. In other words, how many H's fell off times 100. I probably didn't call it an HA initial last year. I just called it concentration of acid. But now we know what that is. So this is very straightforward from last year. Again, 10 to the negative 4.23. I don't know if you came up with a number for that or not. If you did, you can put it in. Over 0.100 times 100. And we have a percent ionization. Percent ionization is really a dumbed down version of the K. The K and the percent ionization tell us really the same thing. They ultimately get us the H3O plus, but percent ionization is a really simplified version. What percentage of the H's fell off? And I'll take that number when you get it. Yeah, what do you got there, Ben? 0.059%. Significant digits. Probably could have handed an extra one, but it's not a big deal. It's a very small percentage. It's weak. All right? Determine the H3O plus and the pH of a 0.1 molar acetic acid solution, given the Ka for acetic acid is. Bang, there it is. Really, if you're doing it properly, you should do a check for the approximation, even though we're not going to use the ice table. I'm not worried about seeing the check for the approximation. If you see 0.1 and then you've got a K of 10 to the negative 5, that means you've got 10 to the negative 5 on the bottom, 10 to the negative 1 on the top. You've got thousands. You're into the thousands for the approximation. So this is weak. So when you get to the 10 to the negative 2 and 10 to the negative 3 in the Ks, when you got to start worrying about it, you might have to do a full ice table. Determine the H3O plus. We've got an equation for that if it's weak. H3O plus. Now forcing you to remember, what's the equation? What is the weak acid equation? A non-veteran. We just use it. Forcing you to think about it. What's that equation we just used? Christian's actually going to just think about it. It's great. He's not even going to look at his page. What do you got, Christian? HA initial. Yep. That's going to get it for us. If it's truly weak, that shortcut will get it. And then you go straight down to pH. Don't clear the calculator. We love to clear our calculators. Not once, but I bet if I did a survey, it's 5. Clear, 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 clear. Maybe it's not. Maybe it's more 3. 1, 2, 3. Or 4. 3 or 4? 4. Because you think that one's faulty. Got to push it harder. It's a strange thing. I don't know why that is. Percent ionization, H3O plus over HA initial times 100. That's just a percentage. I'll take whatever you got. Yep, Tyson, right from the top here. Did you take the square root of that? Here, let me write 6 square root, and then you can tell me what that answer is. Then what do you got? 10 to the negative 3. And this is now a moles per liter. Units would be very nice. Did we get a pH from that? Yep. 1.003, so just 1 is good enough. Sorry? We don't like that? Actually, no, that can't be the case. Because it's got to be between 2 and 3. 2.9? Ooh, I don't like 2.87. Because it's got to be between that 2 and 3, right? How about percent ionization? We want that number over the HA. Over 0.10 times 100. What's the percent ionization? Yes? 1.34%? Okay? All right, do another one. What concerns us about this one? Something should be concerning in this question. If we're a fan of the shortcut, what are we concerned about, Shauna? It's not really small, is it? That Ka is not very small. Let's do a check for the approximation. Let's just do it even first. So it's going to be what? 0.050 divided by 2.8 times 10 to the minus 2. No, this isn't going to work out for us because that's minus 2 already. Over minus 2 is going to get me 10 to the 1. I'm not going to be greater than 100. Can't use my shortcut. What is the number? 1.8? 1.8. That's not greater than 100. What do we need to do? We need the full life table. We need to get that equation that was there before we canceled the X. Again, notice it just says in acid. That doesn't matter. HA, H2O, H3O plus, A minus. We actually could put numbers in this. We really don't need to carry around that HA when we do this. We could say 0.050, that's liquid, 0. Again, we're solving for X. All right? So again, we will be solving for X. Minus X, 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 because it's shifting to the right. 0.050 minus X, X, X. And as you might suspect, this is going to turn out to be not so nice. 10 to the minus 2, X squared, 0.050 minus X. What am I going to have to do here? Jess? Yeah, it's going to be quadratic. There's going to be no way for me to take a perfect square. There's no way for this to work. So let's just, I guess, this is me rolling up my sleeves. No? All right. Let's just do this, I guess. 2.8 times 10 to the minus 2, 0.050 minus X, X squared. So now I need to FOIL that guy through. I can do the minus X part, 2.8 times 10 to the negative 2X. And I need this 2.8 times 10 to the negative 2 times 0.05. What do you got? Sorry? 1.4 times 10 to the negative 3 equals X squared. I like positive X squared, and it is on that side, so we'll bring everything to the other side. X squared, that's going to become plus 2.8 times 10 to the negative 2, and that's X, and that's going to then be minus 1.4 times 10 to the negative 3. A is 1. B is, and you know what, we could get it out of scientific notation if you'd like. You know what, to be honest, I would likely do that. I'd likely write that as 1, 2, right? So I'd likely write it as 0.028 just for the ease of it. You can put it in the quadratic as scientific notation, but I personally wouldn't, because that would be just a pain in my calculator, pushing all that exp, right? C then is going to be negative, and that's 0.0014. And I'm not going to do it. You guys do it, because I'm out of space. And those of you who have the magic calculators, where you put in A, B, and C, and it does it all for you, kudos to you. Nice job. Are those notes from last year? Did we do this calculation last year? Excellent. Sean, what do you got? 0.0, sorry? 54. What's the other one? Oh, you just got that one and you like it? I guess it's going to fulfill our requirements. Actually, no, it's not. It's going to be no good. That's too big. It'll be negative here. So we don't like that one. We want the other root. This one's already getting fired. You're concerned? We don't like that? That's not what we got last year? This should be a negative value? Negative? We don't like that either. Still no? We didn't get one of those either? What are we getting out there? 0.026 and 0.0259? Excellent. The math from last year is the same as the math from this year. Shauna, what did you get there for both of them? Tell me. What did you get? 259? Really? Is that what we're getting? They're the same number? There's just one root? You mean we could have did this with some kind of goofy something? Something's not right. If there's only one root.
The first one.
The first one was right, and it was negative, and we don't like it, and this one we like. All right, now we're catching up. That's fun. Therefore, H3O plus is 0.026 moles per liter, and in the end, we want the pH. And I hope we don't even think twice about getting pH. Once we have H3O plus, I hope our fingers are already moving towards that log button. Bang. What is the pH? Nobody wants to share the pH with me? Or are we still trying to solve that root? We're still solving the root. All right. John, what's the pH? 1.59. 1.59. Okay? So be aware that if it's not super weak, right? And that's where we've got to be careful with our terminology. I actually have to add more terminology to our concept of weak acids, right? There are weak acids, there are super weak acids, and then there's just kind of weak acids. And this one's just kind of weak. It's not weak enough for us to use the shortcut. All right? Okay. Now, I do have one more calculation, and I wasn't going to let you work. I wanted to talk about polyprotic acids. Anyway, let's do this example. I'll give you that homework, and then I'll let you work for maybe 10 minutes. We'll see, and then I'll make a decision on whether I want to talk about polyprotic acids. I need to talk about things like phosphoric acid, where there are the 3 H's and how to deal with them. And I'll make that decision as you're working away. But we'll do this calculation first. This is a percent ionization calculation in reverse. A 0.1 molar acetic acid solution is 1.3% ionized. Determine the Ka. What's the question? There's nothing behind that box. That's a period right after ionized. .3% ionized is not very high, so this one is weak, but we can get a gauge for that when we get our Ka when we're done. Remember, percent ionization is equal to the concentration of H3O plus over the concentration of HA initial times 100. Really what that means is 1.3% of this became H3O plus. So you can rearrange that equation if you'd like to get H3O plus, but really it's a quite simple calculation. H3O plus, right, comes from the fact that 1.3% of this gave up its H's. So really I'm looking just for 1.3% of the initial concentration. And I can write that down as simply 0.100 molar times 0.013. That's 1.3% as a decimal. All right, I just determined 1.3% of 0.1. If you want to rearrange the equation, you'll get that same thing. If we rearrange the equation and bring the HA up here, it's going to get me my percent ionization number times the HA initial, right? I'm going to bring down the 100 divided by 100 because I'm going to bring it to the other side, and that's going to leave me with H3O plus. Now, what do I have here? Well, I have the percentage divided by 100, which is the percentage expressed as a decimal, times the original concentration of HA, right? That's just a classic percentage calculation. It's going to get me 0.0013 moles per liter. Now that I have the H3O plus, I can put it into that equation that I have H3O plus root of Ka times HA initial, square it, right? Square that guy, bring down the HA, H3O plus squared over HA initial, Ka. .0013 squared over HA initial 0.100 Ka. What do we get? Yep, Jenna? 1.7 times 10 to the negative 5, negative 5. And the actual value on our page is 1.8 times 10 to the negative 5. So our little assumption had a little effect, but that's good enough. That's good. So you can go ahead and start working on those, and I will make an executive decision in about 15 minutes on whether I'm going to talk about polyprotic acids right now or whether I can squeeze it into tomorrow's lesson. Might be able to squeeze it into tomorrow's. Is that what we did? We did it the next day? There you go. I've set a trend there. Okay?